Hi, everyone. So I'm supposed to be talking about the neutron star binary source population, but
There's one.
yeah, there's one. So our statistics are kind of low, and the truth is, from the modeling side, things, as far as I can tell, aren't working out so well. Even that one, the rates are high. It's kind of hard to make the whole story fit. Others may have other opinions, but it's like we need very low kicks, or there's something weird is happening, which is a good sign, but I'm not going to go through it. So this is, we need more of them, we'll get more of them, and we need better theory, and the whole thing is sort of in its infancy as far as matching LIGO observations. So I've taken the liberty of not talking about that, and instead, I'm going to talk about some other things that I find interesting, some things I've done recently that kind of tie into this in a broad way, but aren't really on binary neutron stars per se. So, sorry, if you want to leave, yeah. Okay, okay. So that's the plan. But if you really, really want to hear about BNS, channels, we can talk about that at the very end. All right. So I start, here are some of the papers from the, LIGO-Virgo collaboration on the discovery, and really I just want to highlight the only one that matters up here, which is, of course, the standard siren measurement. And so just the idea that there'd be a conference on these results and there wouldn't be some H0 plots, and I just couldn't take that. So I'm going to spend a few slides on that, and then we'll talk about some other things. Okay, and so to start, since it's a pretty broad audience, I am going to review the whole standard siren story, just because I think you're going to hear a lot more about this in the future, so it's worth just kind of going through. And the key point here for the standard sirens is that, in essence, general relativity calibrates itself. The distance ladder is calibrated by the theory of general relativity. You can just do post-Newtonian calculations, and you just directly infer what the waveform should be, and you can directly infer the distance scale. Okay, so unlike many of the other ways to measure distances in cosmology, this one is just very clean calibrated by relativity. And so what you do in this simple case of a nearby source is you're just solving this very simple equation. Velocity is the recession velocity. That's measured directly as in redshift, essentially. And then d is the distance, which will come from the gravitational waves, and then you infer the Hubble constant. And there's peculiar velocity. I'll talk about that very briefly. But that's the basic idea. So, okay. There are two general approaches to this. So there's a counterpart approach where you say, from the gravitational waves we get the distances right away, but we need redshifts. And there are two ways to get redshifts. One is to actually find the counterpart. So this is a picture from Ito. Ito, if you can just barely see, this is our DCAM, discovery of this little transient. And okay, we can do a bunch of stuff with that, and I'll talk more about that later. So that's one way, and that's the way we use. But there's another way, and everyone should keep this in mind, which is, suppose you don't have this unique counterpart. What you do have is a bunch of galaxies. And for each of those galaxies, you can get a redshift. And each of those redshifts gives you a possible value of the Hubble constant. And so you can do a statistical measurement where you get a bunch of different values of the Hubble constant. But if you do this many times, it'll converge on the right one. Okay? And that's actually the original method that was proposed by Bernie Schutz in 1986. Because there was this idea you're extremely unlikely to ever see a counterpart. This seemed like fantasy 30 years ago. But here we are. Okay. So needless to say, we took the left approach so far. That's what we've done. And 170817 was perfect for this. Very high SNR. We had a good measurement of distance. And we got this counterpart. And we had a host galaxy. But there's this issue of peculiar velocities, which I'm not going to spend a lot of time on. But just to say this one, in some sense, was too good. It's too close. It's unusually close. And because it's so close, the kind of bulk flows, the cosmological bulk flows, mess it up. And so in the future, would prefer to have binaries that are just slightly farther away, which is not something I thought I'd ever say. But in this case, all you do is if you go a little farther away, the peculiar motions more or less stay at the same order, but the Hubble recession velocity gets, linearly increases, and so you don't have to go that much farther to have them be subdominant. Right now, the peculiar velocity, I think it's about 300 kilometers a second is the correction in this case, and that's just below the errors from the distance uncertainty from the gravitational waves. So already, peculiar velocities are an issue, but they're subdominant, and as we go forward, they'll become, I want to say, irrelevant, or at least there'll be something that can easily be compensated for, but we can talk more about that. Okay, so when you do all this, you get this plot. This is, the most beautiful plot. It's amazing that this works out. And okay, we measure the Hubble constant. This is the value we get. The width is due to the distance inclination degeneracy, which I'll get to in a second. And I'll just remind you, this, it's the first time this has been done. Really, this peak could have been anywhere. Okay, physics works, so it should be consistent with other measurements. But in principle, the peak could have been way out, in the tail here somewhere. So this thing is not really working. That's too bad. But it turns out to be more or less right where it's supposed to be. And this is not statistically. The fact that it's right in between the two measurements is pure luck. It could have been anywhere there, but it's definitely consistent, and everyone can see that. Okay. All right. So there's this distance inclination degeneracy, which has to do with how loud the binary is and whether it's face on or edge on. This has actually been mentioned a couple of times. But if you're face on, you're louder, and if you're edge on, you're softer. So if you're face on and far away, it can look the same as if you're edge on and closer. And that's shown by this plot, and you can see that. Because there's that degeneracy, we're not sure about the distance, which turns into not being sure about the exact value of the Hubble constant. And so there's a lot to do with this plot, and there have already been quite a few papers kind of exploring implications of this plot. The way I think about this is more along the bottom line. So there are two ways to do something with this plot. One is to say, well, if you know the inclination, you can do a better job of improving the cosmology. And for what it's worth now, it's just an editorial comment. What's beautiful about standard sirens is that it's a GR measurement. And so if you add in sort of messy astrophysics, you're taking some of the beauty away. It makes me nervous. So it's not to say we shouldn't do that, but we should do it in full cognizance that it makes things much more complicated. But you can do the reverse, where if you assume cosmology, you're now learning about inclination. Or if you have independent distance measures, you learn about inclination. And that is quite interesting. And of course, Ilya has worked on this, and Ido and Duncan have worked on this. And there have been a number of papers trying to explore how we constrain inclination of binaries. And I think as we go forward, that'll really be fascinating from the GRB side. So there's a lot to do there. And I'll just mention that we actually, in this paper, we do some constraints on inclination, doing exactly that where we assume the cosmology. And you can see that for different assumptions, CMB or supernovae, you get slightly different peaks in terms of inclination. And you can see that immediately from the previous plot, because the bands are in different places in your inclination plane. And given that, you might say, well, I have a mild preference for not being exactly face on, and you can argue for that geometrically, or you can say from the GRB, there are indications maybe you're not face on, and so there's some preference for the supernova measurement. But that's not, I would never say that at a cosmology conference, because that would be a disaster. No one should make too much of a big deal about it, but it's suggestive. And the point is, going forward, that may become increasingly suggestive. Okay. All right. So that's the sort of LIGO Virgo result. I think it's really beautiful, but things don't stop there. So I was going to talk now about some other projects. And so like many people, there's been this kind of bonanza. There's all this field, really, there's this new field, and there's all this stuff to do. So this is some of the work that we've done in the last year in my group. And I was just going to pick a few papers and talk about them and try to put them kind of in a broader context. And I should mention that I'm not including any of the work, with the DCAM collaboration that Ido and Marcelli have been leading. I think Raf and Wenfei and Marcelli will be talking about this later. Okay, so I'm going to start with some standard siren-oriented things. And so this is the first one. And so this is work led by Xinyu Chen, who may be around, and she's a postdoc here at the BHI. And what Xinyu has done here is explored what the future of standard siren science will look like. And the question is, really, in this game, and we're just focusing on the Hubble constant for now, it's kind of a simple proxy for all the science you'd want to do right now. In that, the way to think about it is you just want to know, when do you get to the percent level? When do you start to be competitive with other probes, cosmological probes? So, and really, if you look at that difference, you want to get to about 2.5%. So the relevant point is that one, which is design HLV year 1, which is just a few years away. Maybe 3 years away, something like that. So, okay, on the order of that time scale, just from the binary neutron stars, that green curve tells you where you get. And you get to about 2.5%, which is enough to distinguish. If it falls squarely on one result or the other, then this big tension in cosmology, it's not resolved, but there's a huge hint as to the way it's going to be resolved and what the systematics are. So if it falls on the supernova result, then maybe the indication is that there's something weird going on between high redshift and low redshift, and that would be fascinating. If it falls on the CMB result, then the indication is there's some systematics with the supernovae. If it falls somewhere in between, which is probably the most likely a priori given the way this stuff works, then it means there's things we don't understand about maybe all three methods. I don't know. Anyway, we'll see. But the point is that it's not long now before we go from this one first measurement and this first interesting statements about cosmology to something that will really matter in terms of impact on the field, which is great. Okay, so there's a flip side to the result, which is what this tells you, the fact, the whole standard siren game, the fact that it's working, tells you something about gravity. And so I just want to briefly mention some results along those lines. And so here's the idea. So you can ask the following question. And I just think this is elegant, and it shows some of the power of this kind of new field. You can ask, it's a very simple question, do gravitons and photons see the same universe? And the idea here is that gravitons and photons, they're propagating through the universe. And okay, we think they're on null geodesics, and of course, principle of equivalence says they'll do the exact same thing, but we've never measured that before. And so this is a first chance to actually measure this statement and to test the intuition. And there are many different ways to phrase that, and there's already, of course, the collaboration put out results on the speed of light showing that gravitons or the gravitational waves travel at the speed of light to 15 orders of magnitude. This is a variant of that. Okay. And the way, okay, and so first let me give you some motivation. You can say, well, I mean, of course they see the same universe. Another way to say this is, does gravity travel in 4 dimensions? And that seems pretty obvious from this room, but I'll just point out that there's a huge business of modifying gravity to account for things like dark matter and dark energy. And the idea there is, if you can change the properties of gravity on large scales, maybe gravity gets weaker in some ways, and then you don't need dark matter, and that would be great. So it's an elegant way to kind of get rid of dark matter and potentially dark energy. So there's been a lot of interest in that. A lot of the activity happens on large scales. And so then there are all these modified gravity models. And in many of them, you have extra dimensions, or you have something that's sort of equivalent to an extra dimension. You have, say, a scalar field, and there's a coupling, and you get losses. And the way, the preferred term is leakage. The gravity leaks out into the bulk, into the higher dimensions. Some sort of coupling, something happens. Okay. And so if that's happening, if gravitational waves are leaking out, then what will happen is you're observing some source, say 170817. If the gravitons you're losing gravitons, it'll appear dimmer in gravitational waves than it should have been. And so you can ask, does the apparent luminosity of the gravitational wave source agree with the apparent luminosity of the EM source? Do the right number of photons and gravitons, do the equivalent number get there? And so that's what we asked. And in some sense, we already know the answer because 170817 got the right value of the Hubble constant, which tells you that it's at the right distance, which tells you you haven't lost the gravitons. Okay? But what we've done is actually quantify that statement. So I should say this is a paper with Chris Pardo, who's a graduate student at Princeton, Maya Fischbach, who's a graduate student with me, and Dave Spergel. And it's really, I think it's just very elegant. These are the sorts of, it's just nice to be able to do this sort of science, where you just say, okay, in GR, the strain just goes as 1 over distance. If there are extra dimensions, the strain should go as something like 1 over distance to the gamma, some other power, where gamma is given by d minus 2 over 2, which is just a sort of flux conservation type of argument. And so that's the general form. And then you can do sort of trickier things, because in many of these theories, there's actually a screening scale, and then you transition over. So you have these issues of the solar system test, so you have to satisfy the solar system test. So what you do is you kind of have a screening scale, and it's all fine on small scales, and then you transition over to these higher dimensional theories. Okay, and then you get something that's slightly more complicated, but this is I should say, this is all kind of hand-wavy. And the reason is, in many of these theories, it's actually pretty hard to do all these calculations correctly. And there are so many different theories that you can just spend all your time, the whack-a-mole of all the different modified GR theories. So this is kind of just a general treatment, and all theories need to satisfy whatever bounds we get. Okay, and this is what you find. And lo and behold, D is the number of space-time dimensions. I'll remind you that in this room we have 3 plus 1, and the constraint we get is, lo and behold, around 4, which is sort of the right answer to about 10%-ish. Okay? And this is just straight from analyzing the gravitational wave data and comparing it to NGC 4993. So, which tells you gravitons and photons really do see the same background, which is great. And we didn't know that before. Now, okay, you can be slightly more sophisticated. You can say, well, maybe there is this screening scale. What is that screening scale? And again, it's actually very intuitive if you think about it. The screening scale ends up being about 30, 40 megaparsecs, because we know that because we haven't lost any gravitons, it must look like 4-dimensional space-time at least out to where the source is. At larger scales, who knows? As we get more distant sources, this will just get pushed back and back. But this is pretty good, going from we don't know, but probably the solar system works, to now we have a direct measurement of gravitons and that they're not leaking. Okay, so gravity is not modified to cosmological, to at least 40 megaparsecs. Okay, and actually I'll skip this. And how much time do I have? 5.5 minutes, okay. All right, and I'll just mention, you can also do this thing of imagining that gravitons decay. Lots of particles decay. Maybe gravitons decay, again, it's phenomenological, and you can say the decay length has to be 138 megaparsecs, which is pretty large, or that's your time. So These are just constraints on gravity, basic constraints on gravity. If you have a modified theory, you have to satisfy these just from this one event. All right. Okay, and so now I'm going to shift gears and talk about black hole formation just for a couple of minutes. And since this came up a few times, I just thought I'd give this result. This is from a paper with Maya Fischbach, where we've addressed this issue of the big black holes. And I'll just remind you, I think it's easy to kind of forget this, is that LIGO is actually sensitive to fairly large binaries. It goes out to total masses well over 100. And what we've detected so far, up to say 30-ish, is a small percentage of the volume. The sensitive volume, I mean, that's like roughly 10% of our total sensitive volume. So there's a lot more volume out there for big black holes where we haven't detected anything. And so you can ask, where are they? And this has been mentioned a couple of times. And the point is, they seem to be missing. And so we can do an analysis of the existing data and try to estimate what the maximum. So instead of saying there's just a power law all the way down to arbitrarily high mass, you say maybe the distribution actually has a cutoff. And by the way, as Stan will tell you, there are expectations that there is this cutoff from pair instability supernovae, so this all fits really well with astrophysical expectations. And then you can fit for the cutoff, and you get something like 35 or 40 solar masses, which is right around where theory predicts you should be, maybe a little higher. And then that actually impacts your inferred mass distribution. And there's been some discussion of the mass distributions here. But the point is, if you're fitting this mass distribution and you let it go to very high masses, and we don't have anything out there, the fact that we haven't detected anything causes your mass distribution to be steep. So, there's a tendency for this to move over if you don't have the allowance of a mass gap. But if you include the fact we actually haven't seen anything at high redshift, at the higher distances and at the higher masses, then you get moved over. And you end up with a flatter mass distribution. That's just, so it's all this is saying is you need to be a little careful about what you mean by mass distributions. There's some richness in the distribution. There appears to be a cutoff. You need to include that when you do your simple fits. And this is what you end up with. Okay. Oh, and as has been mentioned, what's really particularly interesting about this is it may be one of these ways to distinguish between clusters and isolated mechanisms, because if this cutoff really exists, as Avi's pointed out, then you're going to end up, you don't have black holes above 30, but then if you merge them, you will have bigger ones, and then those might eventually merge in the gap, which you wouldn't get in the isolated model. So it may be a way to check these things or get some estimates for the relative importance of these two channels. Okay, Ben will talk about this later, so I'll skip it. There's been some talk about the spins, and I'll just mention, again, this is one of these very elegant results, and it's related to some of the theories out there having to do with dark matter, and maybe all the LIGO black holes are dark matter, which is, as has been mentioned, if you merge two black holes, you almost invariably get a spin of 0.7, 0.68. Because you have all that orbital angular momentum, it's very hard to get rid of it. Even if they're both spinning maximal and aligned or anti-aligned, it doesn't really matter. You're going to end up with something close to 0.68. And if you have a random assortment, it really is quite close. And these are the sorts of distributions you get. There's like this universal distribution of spins you get from random mergers. And so then you can ask, are the black holes that we're seeing, the component black holes, are they consistent with being drawn from this sort of distribution? Because if they're made out of smaller black holes, they need to have spins about 0.7. And it turns out, there's some evidence. We don't measure the spins so well. It's one of the problems that we've discussed a lot of times. But already with the evidence, what we have so far, there's already strong suggestions that actually they're not at 0.7. Which means the black holes that LIGO has seen so far are not made out of smaller black holes. which again, from the standard modeling perspective, that's not surprising. But if you're a dark matter enthusiast, where you're making all of these due to fluctuations very early in the universe, then it might be surprising that they haven't built up into bigger black holes. And so it's just another constraint. Who knows? But it doesn't. The details, again, don't matter. There's just this robust statement that we get from the LIGO observations that the black holes are, in some sense, first-generation black holes, which is just, again, very elegant and clean. OK, there's some Gaussian process stuff. I'll skip down. Oh, I did want to give a little advertisement for this, which is just, this is with Xinyu Chen and Josh, Matt Evans, who is here in the audience, and Salvo and Jolien. We went through a bunch of distances. Now that we're in the cosmological game, it gets tricky how you define distances and volumes. And so we've kind of gone through this fairly carefully. And so there's a paper on the archive inspired by Holz's paper trying to kind of lay it all out. And Xinyu put together an online calculator. So if you're like, well, how far would I see a 50-50 in O3 or design or whatever it is, you can just go to this calculator, hit a button, and it'll give you all the things. The sensitive volume, anything you'd want to know is all laid out there. So I encourage you to play around with it. It's kind of fun once you start playing with it. OK, so I'll end there. It's just the very beginning. There really is this gold rush. I mean, I think you get this sense that people are pretty excited. It's only going to get better. OK, I'll stop there.
Thank you, Dan. Before we get other questions,
yes.
Can you say a word or two about binary neutron star mergers?
Yeah, so
some of us have thought about these.
Yeah, I mean, so I'll tell you from my perspective, which is from this sort of isolated model trying to make these work. The problem is just the rates. The inferred rate, OK, there's a large uncertainty. We have 1. But we got 1, and naively, we probably wouldn't have expected 1 yet. And so it's just hard to make it all fit, to be honest. So you can, there is this sense you turn the dials and get everything you want. That's what everyone thinks about population. But actually, we're somewhat constrained. And turning all the dials as optimistically as we can, the only way we can get close to the rates that are inferred so far based on one event is by sharply reducing the natal kicks. So maybe that is a hint of something, but there are other observations of natal kicks, so I really hate to do that. And
Fred. Yep.
Fred's gonna.
You're the first speaker to use the word graviton, but of course, what we're detecting now is just classical waves.
That's right.
Is there any chance at all that in the distant future, some interferometer could detect something that actually tells you about the quantum nature of gravitational radiation?
So, yeah.
Freeman Dyson.
Yeah, so, well, there is a number of things. So Freeman Dyson says you can never do that. If you build a detector that can detect a graviton, it'll collapse into a black hole. And he has scaling arguments that basically go through that. Now, that's a fairly general argument, and it's not totally ironclad. It's kind of a scaling, but it's an interesting thing to think about. One thing you could say is if you do detect gravitational waves from inflation in the CMB, that is in effect measuring gravitons, because you've now taken single modes and made them real. So it's one way, which I think, I'm not sure what Freeman would say about that, but it's somewhat indirect, but it is a way to do it. There have been some speculative papers coming up with ways to do it in principle with interferometers, but they're still highly speculative, so I wouldn't take any of that too seriously just yet.
Actually,
Another question,
just
Abby?
one comment about the graviton. There is actually emission of gravitons from the sun all the time, 10 to the 8 watts. And that's due to Bremsstrahlung. Protons collide with each other and produce gravitons, and Steven Weinberg calculated it back in '72 in his book on cosmology and general relativity. So there is a branching ratio to emitting gravitons from the quadrupole moment when two particles collide due to Coulomb collisions. And we have a continuous stream of gravitons of characteristic energy of keV. That's the energy of a photon emitted from the middle of the sun. And if someone will develop a detector for those, that will probe the quantum nature of gravitons, because these are emitted by...
Well, so along those lines, and I do think this is, this question is a very interesting question, just the general thing, can we detect gravitons? So there's another way to do line emission of gravitons, which is through these axion clouds, which you're probably familiar, which is, again, it's a kind of amazing effect, and it's totally legit, which is, if you have a rotating black hole and you have axions of certain masses, you get a cloud of axions, they spin down the black hole, and then you get line emission from the axion annihilation effectively, and you get a line emission of gravitational waves, which in this regime that we're talking about for these sorts of black holes happens to also be in band, which kind of makes sense because the cloud is on the scale of the black hole. So in principle, if you detected that, it's a similar thing where you would get line emission, but you're not detecting single gravitons. It's just a process which is hard to understand without quantization. To actually detect a single graviton might have some Dyson-type arguments against it, except for this caveat of inflation.
But I had a question for you. You showed the Hubble relation, V equal hd.
Yeah.
So indeed, the peculiar velocities introduce an uncertainty to the velocity, but there is also an uncertainty to the distance from weak gravitational lensing.
Yes, right.
Did you estimate how much would that reduce our ability to?
Yeah, right, excellent. So there's gravitational lensing, which just means the apparent size of objects changes, and so the apparent brightness changes, and it applies to gravitational waves exactly the same way. You can estimate what that is, and I just happen to have a paper which does that, which is, it's like 0.08 z times z or something like that. So the point is, the sort of sigma you get from lensing really doesn't kick in until you get past redshifts of a half or so. So for this, it's way subdominant, but for the future, it could become an issue that needs to be corrected. Now, again, if you're focused on systematics, one interesting thing about the lensing is that the mean is always 1. And so it doesn't introduce, as long as you don't have a sort of Malmquist type selection, it doesn't introduce a bias, but it does introduce an added spread. And so for better or worse, all the LIGO, BNSs at least, are way too close for this to be an issue in the foreseeable future. For the BDHs, especially if they're at redshift 2, according to George Smoot, then it's a different game.
We're going to have to move on.
But
Thank you, Dan.
Yeah.
Let's all thank Dan again.